All right, as usual, I will put up notes alongside this video in case the recording is no good.
Are you recording right now?
I'm recording right now.
You should erase.
Well, no, that's good.
I'm just going to wonder what it is.
So yeah, I did way too many problems. So the problems that I don't get to will also be uploaded. There was a request for finite fourier transform from someone who's not here yet, so I'm going to wait. No, let's start with an autonomous system, because they're kind of quick. I don't think you've been tested on that yet this semester, right? So there's kind of a classic example called the predator-prey model. If you read any books, it's like in the first chapter. And if I was going to put a problem like this on the exam, that's a pretty good one to put on, just because it's classic and there's no solutions. So it's easy to test you on everything. So you'll be given something like x prime is equal to a x minus alpha x y, and y prime is equal to minus cy plus gamma xy. So x is the population of prey, y is the population of a predator. So if there's no predators, that means y is 0. We get x prime equals ax. So that solution means it's an exponential growth. E to the ax is your solution. So it means without predators, this just grows forever. And similarly, if there's no prey, that means x is equal to 0. That goes away. So we have this, and we have this exponentially decaying thing. So all of the predators just die out in time. So that's why this model's here. So, you know, where do you start these problems? All these values here, A, C, gamma, alpha, are all greater than 0, and they're all real valued. So when you approach a problem like this, like what's the first thing you would do?
Fixed points?
Yeah, find the critical points.
What's the problem statement?
Solve.
Okay.
Problem statement.
Probably a very important thing to know.
Solve.
Okay.
Yeah, so it's solve for x and y.
Okay.
So you want to do a phase portrait is kind of the idea, and that'll describe everything. So what you're going to do first is you find your zeros of the system. So really quickly you can look at it. I mean, it's not always a good place to start as C is the origin, a critical point, because it's, you know, yeah. Just always check that. It's like, you know, another thing is like if you're looking at a system of equations or something and you're like, oh, like you have to make a guess at a first solution, you just guess y equals x. Like almost always the solution. And if not that, like e to the x. You're allowed to guess this stuff, like just try it. And if it works, that's fine. You can use that solution on the exam. Like how did you come up with that? Like intuition. I got this. Yeah, so the critical points are 0, 0. I think that's kind of obvious looking at it, right? And the other one is we can rearrange x prime. We can pull an x out, and we get this a minus alpha y. And then y prime, similarly, we could pull a y out, and we get a minus c plus gamma x. So that's, I mean, this gives it 0, 0 is very clear there. And then we could also zero out this part here. So we could have, you know, y is equal to a by alpha, and then x, just rearranging this argument here, is equal to what? Minus, how can I not do that math in my head? That's a minus, this is a plus, c by gamma, right? So if you put those values back in, it'll zero these equations out also. So, what do we have?
So those are the two critical?
Yeah, so there's two critical points. All right, so
That's
that's
equal to 0. Y is going to be
Yeah.
Yeah, so we're just, you can zero out this the front or the middle. That's really all it comes down to. So now the next step on this is we want to find the Jacobian of this system here, and that'll tell us the slope of how do these equations work. So we're just finding the slope of these systems. So the Jacobian is just equal to the determinant of the partial, so it'd be like,
Also, y is positive to right. Why? The y is positive to right.
Is it positive? Yeah, y should be positive, right?
Really?
Yeah, minus a by alpha, and then plus c by gamma, right?
So you substitute x dash and y, x prime and y prime as 0,
Yeah.
and then
What?
to get y equal to minus a by alpha, how do you get that?
I just say a minus alpha y is equal to 0.
Yeah, that's why it's positive.
So that goes to the other side.
Oh.
And then it's
Did I do that
and then
wrong?
it's positive.
Jesus. All right. And then this one, yeah, it's minus c plus. Yeah, so that's a
positive also.
positive also. All right.
All solution is right.
Sure. Okay. Whatever. Good. Well, then we know where this point y is actually then, even though these are, because they're all positive real values. So, here's our critical point, and then this is somewhere here-ish. So if you were to be given this in an exam, you'd probably put in real values, like, a 4 for alpha or something like that. So generally what happens is you'll call this like f, you'll call this g. And then over here when we're doing the Jacobian, you can do the partial of f with respect to x, partial of f with respect to y, partial of g with respect to x, partial of g with respect to y. And this expands out in, however many dimensions you're doing. If you have 3 autonomous equations, you would just do 3 here, and then independent variables going this way. And you do your partial derivatives. So I think we can all take derivatives, right? So what is this? We get a minus alpha y, and then with respect to y is just minus alpha x. And then we get gamma y, and then minus c plus gamma x. And now we just evaluate this at our 2 critical points. And then from that, you'll have some information, and we can determine how does this slope around those points react, and then we can go from there. Is this all on the,
Yeah.
is this too far?
Nope.
No.
Nope. I mean, we lose you, but
That's fine. Don't go there. All right, so yeah, we can just do j at 0, 0. And what do we get here? We get a 0, 0 minus c. So those are our eigenvalues. You can just, by inspection, you see that our eigenvalues are a and c. There's not much really else to it. So now that we know that we have these kind of eigenvalues, you can look it up and all that, but we know it's an unstable saddle point. So you'll have stuff going like stuff like that. And then j at c by gamma, a by alpha is equal to a minus a minus alpha c gamma, gamma, A by alpha, and then 0. So C, so our eigens, look, our characteristic of this is something like lambda squared plus alpha C gamma gamma A alpha. So what do we get? Cancel, 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 cancel. So what is this? Lambda equals I root CA plus or minus. I forget what that's called. That's the periodic, like an orbit. What are those called? I forget what the heck the name is for it. Stable center. Yeah. It's a circle. Periodic orbit. Like yeah. We know how that looks.
Both plus and minus, both are stable center?
That's what it works to, yeah. I think it's minus is stable.
Yeah, minus is stable. Plus
And then
positive goes like expands.
positive expands. Well, no, the I makes them.
So it can be stable-ish.
Okay.
I makes it concentric, like goes in circle.
Yeah, I makes it go in a circle.
But the negative sign, like it goes like inside towards the center.
Yeah.
While the positive sign makes it go outside. So it can be stable-ish or.
Yeah. So you could write this and then. Maybe. I feel like you can reason out the minus there. I feel like that's non-physical. I forget why. But anyway, that's the whole problem. So that's relatively straightforward. I'd hope you'd get a problem like that, because they're easy. I know you have a question. I can tell by you pushing your pen to your forehead you have a question.
I'm a little stumped. I cannot remember how, after you get the Jacobian evaluated at these critical points, you then progress into getting your eigenvalues.
Oh, it's just the characteristic polynomial. So if we're at this here,
Yeah.
this becomes, this is the augmented matrix 0 minus this junk, 0, right? So if we call this A, our eigens are always A minus lambda I, right? So I just subtract off minus lambdas there and turn it into a determinant. That's all I'm doing. That's why I said this one's so easy, because it's just A minus lambda times minus C minus lambda.
Yeah.
So, you know, we just know that the eigenvalues are diagonal.
So the second eigenvalue that you got was plus or minus I root CA? Is that
Yeah.
right? So isn't that just gonna circle around and not spiral in or out because it's 0, the real part is 0?
Yeah, that's what I thought.
Yeah.
But I got confused. I'm not confident.
Yeah, I don't think it'll spiral in or out.
Yeah, it should just be like this.
It'll just be here.
No, that doesn't go there. Yeah, so you just have a bunch of these orbits, and they're going to buttress up against this here, and that'll change its shape. And that depends on your values of C and A and all that crap. And then all this stuff just goes like, you know, you could just make this picture as pretty as you want. But that's what it'll look like.
Does the plus or minus I indicate the sign it's rotating, like counterclockwise versus clockwise?
Yeah. I forget which way it works, but it definitely does.
Okay.
Yeah. So yeah, you'll get a face portrait, something akin to that. I have a slightly more complex problem that I'll upload for everyone to look at, where you can throw higher order terms into here. So it's kind of like a retention rate. But yeah, this is just, I mean, if this picture doesn't show you how populations work, what does?
It's the circle of life.
But yeah, it's you can see there's a sustained thing. There's a certain amount of predator and prey that you can have a sustained ecosystem is basically what this is saying. And if not, you know,
Yeah.
that's all it is.
Sure.
Circle of life.
What did you learn today in class? I learned kind of about the birds and the bees, but also everything else.
And I think I've recommended this to people before. That's actually, there's a lot of cool work that's done there. And this stuff's used for like control systems and all that kind of stuff too. But it's in a lot of fields. And Steven Strogatz wrote a book on it called Chaos and Nonlinear Dynamics, I believe. It's
Chaos theory?
Yeah, it's a fantastic book on the subject. If you're just bored and you want to brush up on some nonlinear dynamics, that's my recommendation.
Thank you.
I think you should read it. All right. Okay, so next I'm going to do a series solution problem for Bessel's function. The Bessel function was shown to you. I'm just going to show you how to do the first root, or the first kind, I think it's called, the J Bessel function. But you guys have used this in class, and you don't have any intuition of what the heck is this thing.
We used it in Laplace, I guess.
Yeah, and we used it for, it comes up in cylindrical coordinate systems. The Bessel function is generally your eigen for it.
Solutions to finite Fourier transform questions in other coordinate systems usually have Bessel functions as answers, right? Like,
Yeah.
I didn't fully understand.
Yeah, so if you have something like this, you know, and this is your coordinate system. If you're trying to define an eigenvalue on the radius, the Bessel function is what you would generally use. Right? It's clear. So yeah, but there wasn't much talk of the Bessel function in the class. I figure if you see how it's derived, maybe, I don't know if you'll get intuition for it, but you'll know how to muck around with it a little bit. So you can, I don't know, at least manipulate it. So when you see stuff like the derivative of J0 is equal to like minus J1 and all that, and you're like, what the heck? At least you know the form. And plus, like I said, these are the kind of problems if I wrote the exam that I would do, because it's kind of, every book does this. So it's easy to get a solution. Because other people have done it. I think starting with Bessel did it first. So Bessel equations have this form. Right? Where this is just some free number. Generally, we can assume it to be an integer, but it can be any real number in actuality. You can throw other stuff in there, and there's ways to solve for it. But this is a good problem. So you can solve this via series solution, the method of Frobenius. If we divide through by this x squared, we see there's a singularity right there. So you know that you have to find the roots. And as I look at my notes, they're not good. So I might have to solve this again from scratch. So yeah, we're going to assume a solution from 0 of am x to the m plus r. I think everyone here has written this so many times that you kind of, this is burned into your brain. And has everyone gotten good at writing sigmas over the semester? I know I have. My sigmas are pretty great. Not to brag.
Got a nice little hump to 'em.
That's weak. That one's pretty good.
What?
Oh, the top one looks horrible.
That's
It
horrible?
looks like half a Christmas tree. Festive spirit here.
You draw another.
Man, I feel really bad for anyone who watches this on YouTube. All right.
That's all I can see now.
So I'm just throwing these into the governing equation. But you can tell really quickly that it works out nice because we have this x squared here, so that's going to knock off the -2. We have the x here, so that's going to knock off the -1. The p squared thing's fine. And the only term that's going to get screwed up is this. This term here is going to give you the offset. And that's all we have to do. So it's actually a pretty simple problem. And the tricky part is definitions of gamma functions. So, which is in your notes, so it's fair game to throw on the exam, which sucks. Gamma functions are your friend.
No, they're not.
Is this like the friend that also just like sells you something random and white in a bag?
What?
You guys ever have these friends?
What are you calling?
I'm here for this YouTube video.
All right. So this is the term here that's been adjusted for the x squared. So it was originally r plus m plus 2, and I re-indexed it. So now the summation starts at 2, which means that we have to take the other three terms and do their summations we have to do a0 and a1. And once we have a0 and a1, we can then define some kind of recurrence relationship, and that's basically the whole problem, right? So, So yeah, this is for m is equals 0, m equals 1, and this is for the remainder. I'm just dropping off all the summation stuff. So from here we can find our roots, and they should be pretty simple to find, right? So that's pretty cool. There's not much going on there, it's an easy one. And like I said, this is going to be the order of the Bessel function eventually, so if you were to set this equal to 0 and you solve it, that's for J0. Which sounds like a rapper. So we could just rearrange our equation here. And we get this is our recurrence relationship here. And let's just take the positive root first on that. So we get what? AM is equal to, what am I saying? R is equal to P. So we get P plus M squared minus P squared. So what is that? P squared plus 2PM plus M squared minus P squared. So this whole thing is two P plus M times M There's a couple things. So this is just our recurrence equals AM. There's a few things you should notice really quickly is it goes from m to m minus 2. So it's doing a skip, and that's this even and odd thing that you'll see that happens quite a bit in these kind of problems. So that's good to note. So now we can kind of transform stuff to just even or odd, and we go from there. The other thing to note is we'll say A0 is equal to this value here is valued, but we can set A1 equal to 0 and just not look at those solutions at all. And there's a way to show that, but who cares? You can assume that. That's one of those things that you can always just say assume, because it's not going to come into the solution. So instead of worrying about it, you can just zero out all of the odd terms. All right, so where am I at? Let me come back over here. All right, so like I said, we can assume that it's only even terms we're working at, which means m is equal to 2n. This is the definition of even. I talked about this last night at dinner with a professor. It was, is 0 even or odd? No, it's even. That's what he said. I'm like, no, it's even.
Yes.
Right there, boom. How do you know? I thought that was obvious.
What happens if n is 1/2?
That's an
I
integer.
know n is an integer. So the determination of m came from solving for a of m, or that was just assumed?
Yeah, no, that's from solving for this.
Okay.
Yeah. But, like I said, we can see that it's going to be just even stuff. Because we have a value for A0, which is even. And now we can march forward, and we can cast it this way, and it'll ease stuff up a little bit. You don't necessarily have to do this. It just makes it a little nicer. So we have a to the 2n is equal to minus a 2n minus 1, all divided by 2n 2p plus 2n. And now I'm going to do annoying algebra. We can pull this 2 out, so we get 2 squared n p plus n. Now, normally I've shown this to everyone a lot of times of how I would do all this stuff. Is we know that this is going to happen n times, but this p kind of mucks it up a little bit, so you actually have to expand terms. But a to the 2n is equal to, so we know it's going to be minus 1 to the n. We're going to get this little flicker, right? And we know it's going to be 2 squared n. That's going to happen n times regardless. And then this n here, there's going to be n of those, so we still get this n bang, right? We get a0 also. The issue comes in as we get this 1 plus p, and then 2 plus p, up to n plus p, right? But we don't know what p is, so that's why we can't really do anything special about it. But that being said, this is actually a good form. That's good enough.
That's 2 is 2.
That's, yeah, 2 to the 2n.
2 to
2 to the 2n. Yeah, so now, like, honestly, if you got to this point and you use that as your solution, you'd probably be good. But we'll clean it up a little more, just because. So now I'm going to do stuff that I don't know if I'd expect you to be able to do it on an exam, just because it's not intuitive to me. Maybe it is to you. So we have a definition of the gamma function, right? This is in your notes. I think I may have lectured on the gamma function a little bit earlier in the year.
Yeah.
So if we have that, and we make the obvious choice, clearly, that A naught is equal to this, yeah, that's the face you should make. There's nothing obvious about this at all. So if we look at that, and we could define, so this is why this is chosen. We could do this times this jazz here, right? What is that? 2 plus p dot 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 np, right? So that's actually equal to p plus 2. This term gets absorbed is basically what I'm doing. I'm raising the index by 1. And then, you keep doing that, and it comes down to it's n plus p plus 1 is our gamma function.
So that A0 is 1 by
1 divided by 2 raised to the p
that's
gamma p plus 1.
and where did it come from?
Well, where it comes from is we want to multiply this gamma function times all of this stuff here. And that's what I showed here, is if we multiply gamma by all of that, we can reduce it down to gamma of n plus p plus 1.
So is there a formula or something?
Yes,
Given? Oh,
it's this formula here.
X of.
But like I said, if you wrote this as your final solution on the exam, that'd be,
But will we be given that thing? A naught?
you would be given something like that.
A naught 2?
Probably. I'd give it. So now we could say that y is equal to the summation. Let's do n is equal to 0 minus 1 to the n divided by n factorial gamma n plus p plus 1. And then we have x, there's a 2 on the bottom, 2n plus p. So that's actually jp of x. And then there's another definition we can use of gamma, just to finish this all up. Gamma of this crap here is just equal to n factorial. So that just means that this is n plus p factorial. So if we go back, so that's our final solution for our first order Bessel function. And now that I look at it, if you would have just done what I've been saying to you for a couple months doing these problems, and we didn't expand this stupid term here, and we just wrote n plus p factorial, because we know that's going to happen n times, as how I've suggested many times when doing these problems, you skip all of those definitions and you arrive at the same answer with much less effort. So do it this way. Don't listen to anything I just said in the last 5 minutes. Do it the easier way. But yeah, that's what your Bessels look like. So now you have some kind of, so J0 is what we would use in cylindrical coordinates as our first eigenvalue. I'm sorry, eigenvector. So that would just be set p to 0 here, right? So this goes away, we just get n banks squared, x to the 2n. And now if you take a derivative of this, you can see how all the other stuff falls into form. And that was the whole point.
So we calculated the whole thing for taking r equal to p, right?
For,
R equal to p.
yeah,
So what about the minus p?
I don't have notes for that. It's very similar, and you can find it online easily if you look at this stuff.
So
I mean, it's like a very
do we have
classic
to calculate
exam.
both of them or just
You'll never be asked both on the exam. Not in my experience. So, but with it's easy. It's very similar. That's all. I mean, yeah, it's not too bad. It's basically, I think it works out to actually just this. But don't quote me on that. That could be wrong. How are we doing on time?
You got 10 minutes until the hour.
Okay. How are we doing on battery?
Okay.
Pretty good, 50%.
That's nice. I feel like I should do an advertisement and see if I can get ASUS to give me money. Their batteries are so good. Oh, okay, cool. I will do a defective eigenvalue problem. So these are exponential matrices. And you haven't been tested on this yet?
Is that the e to the ta thing?
Yeah, that's
Where
the
you
e to
can't
the-
diagonalize? Yeah.
Yeah. So if it's non-diagonalizable, what do you do?
the exponential one?
Yeah, so I'll go through those because that's, if you haven't been tested on them yet, it's a good thing to be tested on. And if you haven't done them recently, they're very easy to screw up. That's what I'll say. So let's try one of those. I have two examples, one that's kind of simple and straightforward, and then one that stinks. But it's not too bad. So I've done this now for 2 exams of like, oh, these are the problems I put on the exam. Have I been right on any of them?
I don't think so.
I don't think so. I don't think I guessed any problems correctly. Jaworski probably watches these videos and is like, oh, I can't put that on there. No, I can guarantee he doesn't watch these. Okay, so the problem statement would be something like, solve.
This is what sort of problem?
E to the ta.
Yeah.
You can't diagonalize them. I'm giving stuff in.
I think I've done this problem before. Right. So the first thing you always try to do is diagonalize A. And you'll see that you can't, so we'll just jump right in. Find our eigens. Values and vectors, they're both good things. So we get what? -2 minus lambda, 1 minus 1 minus lambda equals lambda squared plus 2 lambda plus 1, right? Is that right? I have the answer here, I should be able to. So that's lambda plus 1 squared. So we get this repeated multiplicity of 2 on that, right? So we'll put this back in, we'll find our eigenvector, so we get what? A plus I. It's better. A plus I times B is equal to 0. Is what we want to do. So we get what? -1, 1, -1, 1. So I think you guys have done this stuff enough that you can see that that's the vector, right?
Shouldn't
The
it be A plus
eigenvector?
lambda I?
What's up?
Shouldn't that be E plus lambda?
Here?
Yeah.
Oh, yeah, but
Just plug that
it's
minus.
just, it's -1.
Um,
That's all, yeah. So,
And V is our eigenvector.
yeah, call it V1.
V.
Make it sound slightly more futuristic. So the idea is now, how do we get a second eigenvector? And it's if you do this kind of a matrix of A plus I V2 equals V1.
See, he never put that in the notes. Like, he had us do this, like, really long, like, integration method thing. But can we just do that?
You could just do that.
Okay.
Yeah. I show this way because that other long form is a long form, and I don't like that.
Well, it's so easy
So-
to mess it up, too.
But there's an article somewhere on the web called like 19 dubious ways to solve exponential matrices or something like that. But it just goes through, I mean, there's a lot of ways to do it, so. And I'm actually going to show another way right after this of how to solve it. Take a knee. So your augmented matrix is the same, and then on this side we get this 1, 1. So we get something like A plus B is equal to 1. We'll set this equal to 0, and we'll just get V2 is equal to 0, 1.
Can you explain the A and B?
Oh, I'm just saying that it's A, or X and Y, or whatever. They're just my variables.
Like across the top, because it's got
Oh,
pins
okay.
on that.
Yeah, or C1, C2, or whatever the heck you want to call them. They're just some things. So this is your second eigenvector, right?
I didn't get that whole thing, the second eigenvector.
Oh, so I just reduced this thing down. So it just becomes what? -1, 1, 1, 0, 0, 0. So we choose a vector for this. So I just arbitrarily set A equal to 0. You could do it the other way if you want. And it doesn't make much of a difference when you come to applying initial conditions, which I haven't provided here. So now, most importantly, I should show you the form of how to put this all together to make sure it's good. So it would be U is equal to C1 e to the minus t, because our lambda is -1, times V1 plus C2 t times e to the minus t. And this is how you take care of the linear independence. Plus e to the minus t of V2. And that's it, that's your solution form. So if there was a multiplicity of 3, you would just, this would become, you'd have a t-squared term and you would keep repeating stuff over. But it's this kind of form, so it's V1, V1, V2. This is an easier form in my mind. And then if you had initial conditions, you apply them for whatever the heck you get. And then, dancing. So that's not too bad, right? So I did one that is worse. So we can do that next.
Can we apply this to the 3x3 matrix too?
Oh, that's a good question. So that's what I have. Yeah, you can. I think it's just something about how the example in the notes is written.
It's just
That's unintuitive and confusing and chunky. But it's not, it doesn't read well, So like if you're trying to use that as like to find an algorithm to solve it, it's almost useless in my mind.
Is it just me, or does he usually give like a x naught for
Yeah.
non-diagonizable systems?
Yeah, that's, yeah.
So where would the x naught come into play over here? Or to solve our C's or something?
Yeah, that's exactly what it would be. So yeah, I don't know. For that, you'd say like x naught equals 0, 1. Sure, that's good, good initial conditions. Just something like that. But that's all it is for. It'll be a vector as long as your system of equations.
But to solve the C's, do we have to do like a k inverse x naught or something, or?
I don't know what you're talking about. So let me write down.
Like you see how they're like in the example we just did, there are constants out there, right?
Yeah, so u is what? C1 e to the minus t 1 1 plus C2 t e to the minus t some crap plus e to the minus t our other vector. And we'll say u at 0 is equal to 1 0, right? So that's just equal to C1 1 1 plus C2, that's 0 0 1. So you just solve that system there, and that's it. I'm not quite sure.
Yeah. One second. Yeah, you can go ahead.
So what is that? C1's 1, C2 is 0. Yeah, C1 is equal to 1.
C2 is minus 1. C1 is 1.
Minus 1, yeah. All right, so there. This is what always happens to me is I screw up my notes. This is a 3-pager. All right, so I'm going to do another, I'll do a 3x3 matrix, and then I'll do a non-homogeneous finite Fourier problem, and I think that'll wrap it up. And then I have some other stuff. I did like a Riccati problem, but I don't think I have time to get to that. I actually did like 4 or 5. But like I said, I'll put them all up on YouTube, so you can just read them there, and then maybe you'll get lucky and there'll be an exam question. I know that. Solve. Right. It's gorgeous. So the first thing you're going to try to do is like find the eigens and see if you can diagonalize this thing, right? So as always, you call this A. No one's called a matrix anything else ever. I'm just going to give you the solution. I'm not even going to act like I'm solving this in front of you.
Did you consult your accountant or your advisor, aka Mr. Matt?
Possibly. Possibly, yeah. So yeah, you just have this lambda equals 2 with a multiplicity of 3. So you can see very quickly that you can't use this standard form. So we can do a minus 2I, and that will give us an eigenvector. Well, actually, write out that matrix. And this, it reduces down, trust me. And it'll give you V1 is equal to minus 1, 1, 1. So if you were to slap this thing into MATLAB, you'll get this vector 3 times. Well, it'll be divided by root 3, because they always do normal stuff. But that's what you get. You'll get that 3 times, and that's not good. So this is here we got our solution of y1 is equal to e to the minus 2t times 1, this jazz here, right? Positive. So now the idea, another way of doing this is we can look at this squared and use this multiplicity to find another eigenvector. And actually, calculating this is pretty easy. So we'll call it u. So you get u1 is equal to so you get these 2 vectors out of it. But I'm just going to, we'll pick this one. So y2 has a form like e to the 2t, and then what we got? I plus a minus 2i times t u1.
We're not using the same.
And this is the form that's given to, this is a different method. But this is the same form that's given to you in the book. It's just a clear way.
Shouldn't be e to the minus 2t?
No, lambda is equal to 2. Right?
Okay.
So the
So e
reason.
raised to, sorry. So it's e raised to lambda t or e raised to minus lambda t?
E raised to lambda t. I hope.
Yeah.
Yeah, the e to the lambda, yeah.
Okay.
This squaring, the purpose for that, just because
This method.
it's a process, it's just something. we
It'll
wanted
give
to
us
do.
another vector
Mhm.
that we can use
Is this in the notes?
in this form here.
No, this.
No, this is from that stupid paper of like 19 it wasn't stupid, it's good. But 19 dubious ways to solve exponential matrices.
So, can we do that with the method that we did before in, like for the 2 cross 2, like a minus 2i is equal to the previous vector?
Yeah, we could try that in after this way. But I think I actually attempted that and I got bored and I stopped. It's not a good answer. Yeah, so we could do this again. And you can cube it. We'll call that vector W. And that just gives us this. It's a zeroed out matrix. So any eigenvector you want will work, right? You can just say anything travels through this space. So we arbitrarily you can pick 0, 0, 1. I forget why I picked that. I think it's because it looks different than what U1 was and what Y1's vectors were.
So when you squared and cubed that matrix, you got those results like using your computer, right? Like you didn't use any trick to figure out what that was, or do you?
I computed it. They're pretty easy to compute by
Okay.
hand.
Okay.
Yeah. Like there's not. Yeah. So I mean, this is just.
I didn't know if like because there's like a row of zeros or something.
No. That's.
And that power form that you're multiplying by is.
It's just this matrix here is right? And when you square it, it's just like squaring anything else, and you just go. Yeah. So you just do this That's relatively simple. And then for cubing it, I'm not writing that out. You know what a cube looks like.
Yeah.
So now I lost my place. Yeah, so we could just choose this, and then we have y3 is equal to this form of e to the 2t. And this expansion is in your notes, right? So it's I plus a minus 2I t plus 1/2 a minus 2I t squared, right? Squared times w. And this is just the definition of an exponential matrix, right? So, like e to the x is equal to the summation x to the n by n factorial. And an exponential matrix has the same, there's a reason why it has that same thing. So we're just casting that out. You know, I guess I should have. Right.
So our final solution is y1 plus y2 plus y3 or just y3?
y1 plus y2 plus y3. And I'm looking at my notes now, and I see I applied the initial conditions, but it's just going to be me like zooming through this stuff really quick, and you're not going to gain anything from it. I just wanted to show you that you can just write out these forms, and it's a little bit, at least for me, it was a little easier to work on that problem.
So all of the, like y1 through y3 would all have undetermined coefficients that could be solved for using initial conditions?
Exactly.
When you add all of them together?
That's exactly what. Yeah. So like I said, these notes will be online, so you could just go through it there online. I'll put them up at some point. It takes like an hour and a half to upload a video to YouTube because these videos are way too big. All right. So if people want to leave now, I won't be offended. I'm still offended that Megan left earlier. And I'm going to do one more problem.
Finite fourier?
Yeah, that's what I'm going to do. Because I tried doing this.
Maybe two? I guess.
Huh?
What?
Keep erasing. Yeah, I have 20 more minutes until my parking meter's out. So I got time. Put this on real quick. Oh, that is so dumb.
Oh, did you guys get?
He did a whale in the gift exchange. I've always wanted to do that.
That is
What's going on?
like some kind of alcoholic.
Why opening it up now?
Oh.
I said last night he was gonna do a problem.
That's so dumb. I'll do the problem in this because it looks like a lifting
Oh,
belt.
wow.
But
Viewers gonna enjoy it.
yeah, that's great.
I saw one where it's like a belt buckle, and like the whole belt buckle just flipped down and it's a couple
So depending on how people do this stuff, every now and then you'll have people like physically draw the problem and put the boundary conditions on it. Or in your notes, the boundary conditions will be written something like du dy equals 0 at y is equal to z. And so they're the hardest boundary conditions I've ever read in my life, is all I'm going to say. So I don't like that one. So inside here we can do that. We have du dy equals minus x on the top. We have u equals 0 here, u equals 0 here. I don't have any fluxing going on. We could solve that later. 0, pi, 1. So I'm using almost all of the values that are known in math. If I somehow can mix E into that boundary condition, that'd be cool.
Or two.
A 2? 2's don't exist in math.
That's always one of those options. Right, 0, 1, 2, pi, or something else. Right.
Yeah.
I guess you got the squared in there, so that counts.
Yeah.
All right, so this is just the Laplacian. Every now and then you'll see it written like this, or you'll have an ambulance, or big delta instead of the ambulance. Just in case you're reading something. These are equivalent statements, that's all that means. I think the Germans started that. So, right, so this is our governing equation. And we're going to go through the same kind of stuff we've done a lot of times already of, you do separation of variables, you'll have this separation variable. But I'm not going to go through it now because I think you've all done that before enough times. And then we just, we have u is equal to some xy, right? I did this out of order. You assume this, you put that into there, you get separation of variables that looks like that. It's different in different coordinate systems, but I picked a rectangle because everything's a rectangle. So Colin, how would you start this?
I'd look at the x double prime over x equation, and I know that would go into a form of C1 cosine minus lambda x plus C2 sine lambda x.
Yeah, that's pretty close. So the reason why you do that direction though is because if you look in our x direction, in the x direction we have these homogeneous boundary conditions. So we don't have to do more transformations. Whereas in the y direction we have, it's homogeneous down here at the origin, but up here it's this minus x, so we have stuff fluxing in, right? I don't know what it would be. Something is coming in, some x. So yeah, we could solve for that.
Is this?
So this isn't finite Fourier transform, right? This is separation of variables.
Oh no, it's finite Fourier transform.
Oh. I thought, well.
You have to do all of this crap
Oh, because like I thought
there.
to get
the
there.
eigenfunction. I thought we could use that table of
Table, yeah.
eigenfunctions.
Yeah, but where's the fun in using the table?
Fair enough.
Come on. You should know how to derive this stuff in case you have to do it. I mean,
So we're doing.
they don't just
separation
give
of
someone a
variables.
belt like this if I look it up at a table.
So you're telling me that everything we're doing could be just solved by using that table? I'm
Yeah.
just not to like.
Yeah,
Okay.
these next few steps are, but this is a Sturm-Liouville problem,
Yeah, I
right?
was gonna say, this is also about.
This is Sturm-Liouville, so you should know how to solve that. It's just,
Two birds with one stone.
I think it's the easiest Sturm-Liouville problem you'll solve, right? Is
I think it's that a cosine. It's my
this,
star equation.
right?
Yeah.
And that's just a very easy Sturm-Liouville problem. The weight's 1. There's a P and a Q. I forget what they are. I forget the order of Sturm-Liouville off the top of my head. P is 1.
Well.
Q is 0.
Yeah.
Sturm-Liouville. All right, so I assume you know how to do that. So we could just say something like, I'll just cut right to the chase of, I didn't write.
Wouldn't we have to transform our boundary conditions? Wait. Oh, no, never mind. Just one second.
Lambda n is equal to n plus a half, right?
Oh, last problem.
So normally, this is why. So normally what you do is you divide, this would be times pi, and it's over the length of your domain. But the length of our domain is pi. So that goes away, and you just get this, right? So up until this point, this is the lookup part, right? For the people who don't want to be cool and solve the problem themselves. So this is our eigenvector in X, right?
So those will depend on, like, if you were to use the table, the criteria for looking these up are the boundary conditions, correct?
Exactly. Now I forget what the table looks like. I don't know if it's all on the unit from 0 to 1 or is it 0 to L. But that makes a difference. So yeah, so we just defined, to bring you up to speed, Jordan. Here's our problem for finite Fourier transform. I held this to the end just for you. And this is our governing equation. We have Laplace in here. It's homogeneous in the x direction. U equals 0 here, and it's du dy at the top is equal to minus x. So this is the inhomogeneity that we're going to have to deal with. So, from here we defined our eigenvector, and we're just going to take that and multiply it by the governing equation. Do a couple integration by parts and a little bit of manipulation, and then we can evaluate everything. And then we're going to get, what's going to result is we're going to get some equation in y, and then we'll use this information here to set the boundary conditions, or the coefficients there.
Did you get that stuff that's in this box there from?
Yeah, this is the table.
Just table?
I don't know.
So is that X that you have there, the same thing as the?
What do they call them? The feed? Is that feed?
Yeah.
All right. Yeah. So now we can just do.
Jackson and myself.
What?
Last one, sorry.
And if we had some kind of like flux on the right hand side, like a Q, you'd also transform that here. Whatever our Q of X and T, or no, there's no X and Y and whatever. But that's 0 for our case, right? So we don't have to worry about that. But what happens is this reduces down, so this will just be a kind of a ODE, and then if you have this Q here, you basically have to find a particular solution, right? So it's nothing, it's just a little more painful, but it's nothing too garbage.
And those are both in the
People.
X.
Yeah, so we integrate from 0 to pi. So what we're doing is we're just going to stack up eigens, basically, all the way up and down is what we're doing. And then we have the system. So x is strictly dependent on x. So we have that x du dy squared term there. But we could just manipulate that to have it be, so this term here is actually, we can just equivalently say, I should put a dx there, d squared, dy squared, integral 0 to pi, it's all of this stuff, x times u dx, right? And this is our transform. This is our Fourier transform. So let's call that UN. You guys feeling tildes or hats?
What's that tilde look like again?
That's the correct answer. UN tilde. So that just becomes. Yeah. Yeah. So it's Senor M. So that's a simple transform, right? Well, we don't use tildes in English, do we? But Spanish uses them. If it was an umlaut, it would be
German. So
So now this is the crux of the problem then, is kind of going through this transform. And we have two derivatives here, so we're going to do integration by parts twice to kind of peel that off. And then we're going to use this definition here at the end, and you've done this stuff before, right? So it's not anything too crazy.
It seems like we've always solved very similar, if not exactly the same format, and all that really changes these problems is boundary conditions and initial conditions if provided. Is that kind of how it's probably going to be on the exam?
Yeah.
Okay.
But he might give you a crappy boundary condition, like a mixed boundary condition or something like that. That's what we got. And that just makes...
Were you able to look that up on the table, or?
I don't remember. Probably.
Is that where you solved for the harder one and it actually worked out?
So in the equation, right there, you have is equal to integral of 0 to pi x. Is that part of the problem, or is that the line above it on the right side?
This? Oh yeah, but this we didn't have a q, so it's just equal to 0. I was just saying if there is a q, you'd also have to transform that stuff.
So we're operating the two axes here. They're both finite spatial axes, right? So we can transform either of them, but let's say we had one spatial and one time dimension, and we assume time is infinite. If we were to do a finite Fourier transform, we'd have to operate on the spatial axis, right?
That's what I would do. I'm trying to think if you could do it the other way, and I don't.
Because it's finite, right?
Yeah,
That's what
finite.
dictates what you can transform, right?
Yeah.
Okay.
Yeah.
So maybe if you did it in finite time, discrete. But I'm not sure.
Okay.
I've never tried the other way.
That's what you said.
That's crazy. All right, so what do we have to do now? Okay, so let's do this.
Says if we got 5 minutes.
I mean, if someone wants to feed my meter, I'm at parking space 7259 in front of Pack. If anyone would have taken me up on that, I would have been very confused. All right, so I think everyone here knows how to. I erased all my boundary conditions too. Yeah.
Do you want like 15 minutes, a half hour?
I don't care. I don't think the parking meter ninjas will catch me.
Okay, you got 15 minutes.
Oh, you just paid on your phone? It's a great app. That's the least amount of time you can put on, isn't it?
Yep.
All right. So luckily, a lot of this stuff's going to zero out, right? So we get here. What do we have? X at pi is defined to be 0, and du dx at 0 is equal to 0, right? So this is the definition of our eigen. This is the boundary condition. Here we have x prime at 0 is equal to 0, and u at pi is equal to 0, right? Yeah. So that zeroes all those out. And that's just definition of the eigenvector and then boundary conditions. So we get rid of all those terms, which is nice. If there was some kind of inhomogeneous thing on the boundary, you'll get terms here that come into play. And it just makes it a slightly different differential equation to solve. But it's not anything that you can't deal with.
You got to that line by doing two separation of variables.
This is two separation of variables. Yeah, so it's always going to be a form like this.
Yeah.
I might even recommend that you have that as your note. You're allowed to put notations. I maybe would write down what's the two separation of variables in cylindrical coordinates, and then in this rectilinear coordinates. So then if we remember from our separation of variables, jazz, that was our definition, right? So we just put that in. That's what we're left with now, is this minus lambda n squared integral 0 to pi x times u dx. And this here, once again, is our transform, right? So this is senor u. So if we look at it, we get this term here minus that term there equals 0. And this is an equation you've solved it, enough times now that so now you just solve this equation, and you guys can look at that and you know what the solutions look like. You get this e to the lambda y, and then e to the minus lambda y. Yeah, so that's nothing crazy, right? And that's cinches and coshs, which I prefer to use cinches and coshs, especially around the origin, because around the origin, cinches and coshs behave like sines and cosines. So I know those definitions, and when I apply boundary conditions, it's just easier for me to do. But you can do it the other way if you want.
Sorry, could you explain what you did over there with the last integral?
With this one here?
Yeah, with that last integral from 0 to pi.
So this integral here
No.
was this one here?
One below.
This one?
No, so up top from the integration by parts,
Yeah.
the third integral.
Oh, this one.
Yeah.
So I have x double prime is equal to minus lambda n squared x.
Okay, x being our eigenfunction.
This is our, and this is from our separation of variables.
That's always the case.
Yeah.
In rectilinear coordinate systems, yeah. If it's radial or spherical or something, there's going to be r's and thetas and weights and stuff like that. But for that, so what I do is I take this definition and I put it into that integral. So I get minus lambda n x u dx. I just pulled this out because this is a constant. And then this integral here is what's left. And this integral here is actually, this is our Fourier transform. Does that make sense?
Yeah.
So you're gonna, in these problems, it always kind of reduces down to this form. So it makes it nice. And then I just used that, and I put that there, and the other one was this. So this is just bringing it all back together. We get this kind of a solution.
So when you have a solution for un tilde, you have to bring it back into.
Yeah, but we have to solve